you have your assignment written in your plan book and no homework written for tomorrow, please go ahead and get out your math book and look at 231. Anyone ever go spelunking? Whoosh! Hold on, Kate knows what that means. What? Well, it's when you go caving. So when you go spelunking, you go caving. So as you're getting your textbook out, I'm going to set you up for today. In 231, our intro talks about graphs can be useful tools for finding relationships and making predictions. In this lesson, we're going to work with our team to make choices about how to set up a graph in the most useful way. Again, making your life easy. We want the most useful way to build the graph. As we work, use these questions below to help us focus. So listen up for just a second. Does our data fit on our graph? And can we see it clearly? How could we make the data more clear? How could we make a prediction? And then, will a different choice make it easier to predict? Now, one thing that I will go ahead and say, just with the things around my room, the accelerated 7 math class, we already talked about some of this because, they're on the accelerated path. And we made that graph up there. Now that graph on the x-axis, the horizontal, is how tall a person is. The y-axis is their reach when they board a roller coaster, sit down on the seat, everyone sits on the same seat, and they reach up like out of excitement. We graphed this data, and you guys will remember this problem when you get to it next year in your 8th grade textbook. We graphed this problem with some data we collected from the class to try to figure out if you would lose your hands on that roller coaster. It hurts me when she slams the door. So, that up there kind of shows you how we use the data to make predictions. So I want your teams to dive into 106, where we have some data that we could have collected if we went spelunking or went caving on bats. So we are collecting data on bats, which, by the way, one of your roots this morning, or one of the words we talked about, was dissonant. And depending on what class you were in, you might have talked about sonar, one of the roots in there. Bats use sonar to see, which is the root sonari, I think it is, just meaning sound. So they make little squeaks and chirps, and then they get the echoes back. So it's called echolocation. Yeah. Why what? Right, so we were in section 2 of chapter 2. Now we're in section 3 of chapter 2. We've changed topics, enough to be in different sections. So we had 2.1 whatever, first section, 2.2 whatever. Now we have 2.3, and then we have 2 lessons left in this chapter. We are almost done with this chapter. Wow. All right, so you have these resource pages, hopefully. We have some data. Go ahead, check out this problem, attack it as a team, see what you think we can do to solve. Have at it. We'll give you a few minutes. So we are not really using the resource page yet. You'll see on there there's space for 107, 108, 109. Raise your hand if you don't have a resource page. I'll bring you one. Sweet. Perfect. All right, let's give you 3 minutes. We'll give you until 9:15 to check out this problem, talk about the data table, how we might use it to make predictions.
Can we make any like statements about relationships that we see? Like relate this to humans, and we'd be talking about height, and this is our wingspan, right? Talk with me. Do we notice any relationships? Do we notice anything to make predictions? Why did you come? You're on. You guys can really just share one text with me. Just put it in the table. So there's a part of thinking about this over the past 2 days. Like angled, like that, taking shots. So the book is like cropped up a little bit on the surface, but it has to be like one big thing you set down. Or really simple would be like a chunk of 4x4 and crop up the book. Yeah, so like you have a book pointing both directions. Maybe a little page holder thing. A little booklet. All my free. Well, I gotta go Terry that gecko stand. Aquarium stand for the geckos. I wouldn't think it's purposeful if we didn't already have the wood. If you have the wood from the whose clamps are those? Do you have any idea? I took them home. They're really long, like we used to do height clamps, but they're probably Kelly's. Oh, it's not. I mean, not like it was all clean. There was like
these have to decide
what
the relationship.
Oh no, that's
Alright! Let's use cards. They're fun. Keeps you alert, wakes you up. We went through the whole stack yesterday, so now I get to shuffle. Alright, we'll take a volunteer, I guess, for this. Anybody have any observations that you want to share with us? Any relationships you might see? Anything that could help us make a prediction? Liam, what do you think?
Well, Patrick saw this. That with any number, if you multiply it by 3, you get pretty close to the wingspan.
Ooh. So you're saying that the wingspan is approximately equal to 3 times the length? 5 times 3 would be about 15. 3.5 times 3 would be a little over 10. 4.2, well, take off the 0.25 and that would work. This is pretty close. Pretty close. I like it. What else could we say? I agree with your statement. Approximately 3 times. Anybody know the human relationship? Our height compared to our wingspan. Now, these aren't wings, but that's what it's called, is your wingspan. How does the wingspan, distance between your fingers, compare to how tall you are? Make a prediction based off what you see right now. If you took the whole distance, even across my chest, compare it to my height. It should be approximately equal. Now, depending on whether your arms are longer than so I'm a really good swimmer because my arms are longer than they should be. So my proportion, we measured this. When we went to Chicago, if you get a chance to go to Chicago, go to the Science and Industry Museum or Science and Industry Center. I forget exactly what it's called. They have a display right now where a camera measures you. It shows you everything, and it tells you your ratio. So we're saying for a bat, their wingspan is about 3 times. For a human, it would be about equal. What else? What if I gave you, we found this new bat that had a length, body length of 9. What could you say about that compared to the bat with the wingspan of body length 3 and wingspan 10? So essentially what I'm saying is as I go out the x-axis, as my bat length gets bigger and bigger, what would we expect? Alex? That the wingspan, you don't even have to be that specific, that the wingspan keeps going up. Right? That graph up there that we drew, as people were taller, their reach was also taller. hence the line that goes nicely up from left to right, from bottom to top. So now as we look at 107, we want to use that sort of knowledge where we compare values and we see, okay, as this grows, that grows, or as this grows, that goes down, or what comparisons can we make? And we've got some data on the graph. So check out 107 with your team. Peyton has started a graph of her work shown at the right. First thing we want to tackle is which axis represents the length of a bat. So they're saying this coordinates to the data table that you have. So use your data table to try to figure this out. Think like when you look at the graph, what do you notice about the data? If you were trying to make predictions, what about my bat with length 9 or, I don't know, 10 or 12 or anything like that? These are the things you want to look at. Do you think you could make the graph better than this? These are all the questions you want to ask yourself. So, in A, make sure you've labeled the axes. In B, determine what is the scale. If you don't know what scale is, we might need to look it up. Is it appropriate for this graph? Like, does it work well, or would you change it if you were given the option? Take like 2 or 3 more minutes to discuss this. Yeah, you can do this work on that page too. What do you think those axes represent? Up to the points of that, those x values are. What do you think the x-axis represents? What do you think the y-axis represents? Well, yeah, but which one goes where? That's the question. Okay, when we compare the data table that we have with the graph that we have, your x-axis, what did you label that? Sorry, I couldn't hear you. What? So we had, from the table, we had length and wingspan, right? We needed to put those as labels on the axes. So this axis, are the x values the lengths or the wingspans? The lengths? How do you know that? What lengths do we have to work with? 3-ish, 4, 5, that's it? Yeah, 3 to 5. My top point is at 5. If you tried to label that wingspan, if anybody tried to label this wingspan, notice we don't have anything out here near 10 or 11 or anything like that. So this is length. And you always want to put what it's being measured in, so it's in inches. If you did not put inches, please do so. Which means our y-axis then has to be wingspan. And that's also in inches.
So then Zoe, when it asks us what the, what's it say, what the scale of our graph is, like what is scale? If you don't know, that's what I'm here for. So scale is like how much we, well, actually it means two different things. In this case, when we're working with graphs with axes, it's saying how much are we counting by when we move boxes. So every time I move a box, how far am I going? I mean, those are what's marked, but every individual box is worth how much? 1. So although we only show the 5s, our scale is actually counting by 1. Every box is worth 1 because 1, 2, 3, 4, 5 boxes gets me to 5. And vertically, it's the same thing. Here's like a bonus question. Does my vertical axis, my y-axis, have to match my horizontal? Does my vertical have to match the scale that I use? Have you ever seen a graph where the x-axis is one data, like years or something like that, and the y-axis is something else? They have different numbers on them. The scale of one graph axis has nothing to do with the other axis. You can change the scales however you want. So that's what we're going to practice in 108. Because if I ask you, is this scale appropriate for graphing this data? What do you notice about the points of our data? Like Delaney, if I ask you what you notice about our graph, about our points on here, what would you say about their location?
They're all pretty close to each other.
They're all really tight together. And if I look at what section of the graph they use, they only utilize this little chunk of the graph, right? There's so much graph out here that isn't being used. So, one of your classmates pipes up, and they're like, wait, I've heard about this before, right? When the graph doesn't represent things correctly, we can change the Zoe scale, right? So how we count on the graph determines how spread out or how close together it is. So back here, I'll just keep referencing something you'll be able to see anytime you want. Back here, we used 10 centimeters as the scale. Every box was 10 centimeters across, and you can't really probably see it from back there. Every box as we went up was 10 centimeters. But we only wrote every 20. So we wrote 20, 40, 60, 80, and then a couple times we put the inches we converted. But as we move the boxes, we want to label what our scale is. So in 108, check out if we try changing the scale. Sorry, that's 106 again. There's 108. So now check out the graph that you have on your paper and place the points in the appropriate spots. Can we focus for the computer in front of us? Or is it too much? We got extra textbooks.
Wait, draw it on here.
Yep, on your resource paper. So you're going to take this graph at the top right. I don't want to show you that one. It's the answer key. The graph at the top right, and you're going to place your points on it. Here's an easier way. I have it open in a tab. Just to help you, we'll do one together. So if you look at your data table, up on the TV, I've got the data table. And I don't really care about which type of bat it is, so I'm just going to zoom over or move over and look at that. So if I have 514, and we already said, what about the axes for labeling? Because we need to label these axes. What about our axes? What did we label the horizontal axis last time? Length. It is the x-axis, but we called this length. So write length. Oh, that's highlighted. Write length for your x-axis. And then wingspan for your vertical.
if we go to put that top bat on the table, we're going to go to a length of 5 and a wingspan of 14. So length of, what's different about this graph? Liam? Well, yeah, so I need units, inches. To be appropriate, I need units. These are in inches. What's different about this graph? Ooh, now these 5 boxes get us to 10 instead of to 5. So what would one box be worth? 2. So now our X scale is by 2. What's our Y scale? Still by 1. It's still counting by 1s. So if I try to place 5, 14 on that graph, I go to 5, well 2, 4, I have to go in between, and then 14, I go up, 10, 11, 12, 13, 14, I'd be right there. There we go. I'd be 2.5 boxes in, 14 boxes up. Place the other points on your graph. If you're struggling, please stick up a hand so we can help you. Try it out. Help your teammates first. Then stick up a hand so we can help you. If anybody wants to come and put them on the smartboard, you're welcome to come and do it. You're confident with where you're going to place them. Actually, let's zoom way in. Alright, we're just going to cover this up. We want this graph to be huge. But we need to still see it. But yeah, now we can see it. And get that table up here. And we had 14. Right about that. Anyone confident? Want to come put them on? Your hand is first. Sorry, I'll use yourself. Do it. I mean, sure. I mean, there's only 4 more. I'll help you. I'll tell you what the points are as you go. Your next one, 3.5 and 10. So the question we're really going to answer here, does this show our data better? Is it a more efficient way with the modified axis? Right, we changed our scale. Yeah, 3.5 is just below that. You're perfect. That's awesome. Just below that second line. The orientation is off slightly. Yeah, we have 3 and 10. 3.5 and 10. Okay, we have 4 and 11. So there's your 3.5 and 10. The next one's 4 and 1/4 and 12. Perfect. Your next one's 4 and 11. And your next one's 3/10. That's 4/10.
So wait, don't pick up the eraser. Okay. You can move it with your finger, like you can grab the point. So put one in the middle of those boxes, and then one really close to that line. Yeah, they're almost on top of each other. Now, for all the marbles, for the cream-filled donuts, for the whatever you want to think. I have no food. Does this graph, even though I blew mine up like the size of a person, does this graph more effectively show our data? Why or why? Was that Marvin?
Yeah.
He was very adamant. Marvin, why not?
Because it's still most of the graph that's not even being used.
Is this better or worse? Somebody, what? This is worse! We did the absolute wrong thing. We went backwards. We failed. It's okay. Failure's good, right? Growth. So if scaling up, if making every box worth 2 was bad, what could we try now? We already had every box worth 1. Now we tried every box worth 2 on the x-axis at least. That got worse, Marvin.
Make it a half.
Make it less. So if you look at your resource page, hint, hint, nudge, nudge, you should have kind of guessed where we were going. You choose the axis labeling. You as a group choose the scale for 109. Now you still have length on the X and wingspan on the Y, so you might want to go ahead and write those. Length is still on the X, wingspan is still on the Y. I'll get mine up there in just a second. What's the best way we can do this? What's the most efficient, like how much of the graph would we like to use? Like if we have this much space to put our data, we'd like to use all of it. Now be careful, 25ths is not 2500ths, which is actually a quarter. So be careful saying 25ths. Patrick is proposing, what if you make each box a quarter, causing us to go 4 boxes to get to 1. Then 2. Then 3. Then 4. Ooh. Try that. I mean, you can try whatever you want, but Patrick is proposing that'll let us use the whole graph. I'll give you probably 2 or 3 more minutes to play with the axes and get your points on there. I'm talking about the x-axis. Oh, I'm off somewhere. So I'll propose another question. Patrick decided to go by quarters because he could fit all that on, and still, he doesn't even need 5. The highest he goes is 4.25, but having a tiny bit of space left over is good, because then we fit easily. What's the max we need to go to on the height, or the wingspan, sorry, right? 14. So if our max here is 14, we know 14 should land somewhere in the range at the top of our number line. Now, unless we break our graph, which we don't really like because that skews data, unless we break our graph, we need to evenly distribute to get to 14. Does anybody know the method? And there was actually a math notes box on it back in chapter 1, I believe, for how we scale an axis, how we decide what to count by. Could go by, do you mean every box is worth 2? Sass. What do you mean then? No, I know what you mean, but I have to ask those stupid questions because I have to act like, I have to tease out those ideas. I know what you're trying to say, but I need you to articulate it. What do you mean? What should 1 box be worth? 1! Okay, so we're going by 1, even if we mark by 2s. That's not going by 2s. Each box here is worth 1. Like each box here is worth a quarter. Okay, so even though we can mark by 1s, we're going by a quarter. How we can decide how to scale an axis. How many boxes do we have to work with? Well, if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I only have 20 boxes to work with, and I need to get to 14. Could I have them go by halves and get to 14? If I go by halves, where will I end 20 boxes later? I'll only end at 10. What if I go by 2s, I'll get to 14 like here. So, Annika? Yeah, exactly what Marvin said. Stick with your scale of 1. We don't need to modify the y-axis at all. We can leave it how it's been the whole time. But if I follow Patrick's method, for the x-axis, I've gone by quarters, so I'm going to mark a few of these. Here's 4, 6, 8, 10. Make sure you've got a few of these marked. And even though my 14 leaves some extra graph up here, that's good because we don't know if we have actually the biggest bats there are, or if we might want to predict beyond that. Check out the graph we made for the roller coaster up there. And I'm giving away stuff for 8th grade, but you'll forget it over the summer. We left space off to the right and above it so that we could predict. I don't know who Robert Wadlow is. I'll be very impressed because you have no reason to know. Robert Wadlow holds the world record as the tallest man ever measured, tallest person ever measured. So in order to fit his height on our graph, we measured Phoenix Kids. We only went this high, right? And this is me. I'm taller than you guys. We only went that far. If we made that point be the furthest point out on our axis, we wouldn't be able to graph anybody taller. Robert Wadlow is 270 centimeters tall. He's almost 9 feet tall. He's huge. He has passed away. He no longer exists. His reach, we anticipated way up here because we used our graph to predict. So the extra space is good, but you don't want tons of extra space. So, do we have our points plotted? Did we get all 5 points on there? So try it. If you don't have it down, try it on there, and I'm going to quietly do it up here. Then look up here and see if yours matches. Oh, my bad. We do need 5. I misspoke. 5 is necessary. So this is actually a perfect scaling. Problem is we might need to extend our graph up this way since 5 is already my max. let's talk about baby bats. Right? Baby bats. Cute, tiny. I don't know how big a baby bat is. But baby bats are probably pretty small. Now, if we relate this to humans, same question can be asked that I'm going to ask for the bat. If the bat is wee little, what do you think about their wingspan? Probably wee little. So, we could make what I'm not supposed to tell you yet, but I can't resist. We could make a line of best fit. Not the perfect line, not the exact line, but it's the best line. You're going to do this in science, hence why I'm just going to give you that vocab word. CPM doesn't really use that vocab for like another year or two, but the line of best fit is the line that will best go through the data to help me predict. So if I want to try to go through these points, but I assume that a bat of 0 height will have 0 wingspan, I want to start here and go up through these points. Now I know the general way it should look, but then, and this is like where I can cheat with a smartboard, and you should use a ruler because you can see through it, I can then move this slightly to try to figure that out. Now, if I'm actually using a line, like a precise line, I want to try to get it so that the same amount of points are below it as are above it. And that's really hard here. Right about there goes through about 3 of them. I'm going to call this one kind of below and that one's definitely above. But a line of best fit, we normally start right about the origin and try to go up through our data. So then if I ask you, what do you anticipate the wingspan of a 1-inch bat to be? How cute would that be, a 1-inch bat? What would you anticipate for that wingspan? Alex? Right here where that hits, 1-inch tall bat, we'd anticipate a 3-inch wingspan. I knew that would happen. All right, so moving on. So Peyton's got that. Sorry, that's the same page. I forgot that I keep cloning. So 110. We're almost out of time. Predict 2.75 inches using your graph that we just made. Predict if the bat was a length of 2.5 inches. I'm going to go back to that graph since it's super giant. .75 inches in length. Penelope, because we're running out of time, can you talk me through how you would do this? Sorry, is the 2.75 an X value or a Y value? If it's the bat length, it's X, right? So, what do you do?
To find
to make our prediction.
It would be like how.
So I think we're making this more complicated. I bet you already know how to do it. Just explaining it's weird. We go on the axis that matches. Hey, hold up, we're not done. They released early. It's not my fault. 2.75. Find the point on your X. Follow it up to your prediction line, and then from that point go over to make your prediction. About 7.5 likely. So I won't see you tomorrow. Please do your homework. There's only one more lesson, and then we're doing a math journal check and taking a test. So please do your homework. Please make sure your math journal's up to date. Check math. Make sure your past stuff is good. Discovery Day is coming up on us. Outsiders Day tomorrow. Looking forward to seeing a lot of greasers and preps. Socias. Sorry, different genre.
That was a lot of correction for saying so shit.